Hello everyone. In today's lecture, we will continue our discussion on natural gas processing. So, in today's topic, we will cover dehydration of natural gas. When we look our production system, we see when the gas is reaching at the surface facilities, it is meeting separator. The separator is going to separate the phases of the fluid that is getting produced. Based on the separator chosen, 2-phase, 3-phase separator, according to phases are being produced, the water, gas and oil can be separated out. And after this, when the gas which is supposed to be sent to transport by a pipeline to consumer, the gas needs to meet certain specification of pipeline design. And when we see that perspective, the natural gas after the separator is supposed to be treated to remove the impurities present in the natural gas, or some valuable compounds, those are also present in the natural gas. And when we had natural gas, the water that is getting separated at the separator is just a free water. Depend on the composition of the natural gas, like hydrocarbon and non-hydrocarbon gases, the solubility of water varies. That also depend on temperature and pressure condition. So, after the separator or the first unit that is faced by the natural gas produced from the reservoir still carries significant amount of the water, and that water needs to be removed. The process of removing the water vapor from the natural gas is called dehydration process. The natural gas after the separator or the natural gas that is untreated carries few hundred pounds of water per million standard cubic feet of gas, while the gas pipeline normally require water content to be in the range of 6 to 8 lbm per SCF. That is why the water removal is required, because the presence of water in natural gas creates several problems, like the solid hydrate. If the water is present and by any mean the temperature and pressure of the natural gas at any point is falling in the range of hydrate formation, the water that is present in the natural gas will form gas hydrate and it will plug the pipeline. It will create several problems. Not only hydrate formation, the water which is soluble in the gas at a different temperature and pressure condition, the solubility will get changed and it will come out from the gas phase to liquid phase. When it is happening, we are having 2-phase system, water plus gas, and the slug flow will be present in the pipeline or in any flow system, and that will create a problem. When natural gas is having the acid gases and water is also present, it creates a problem, or the water creates a problem of erosion and corrosion. Not only the problem associated with the presence of the water in terms of erosion, corrosion and the phase changes, the water that is present in the natural gas, if it is getting transported from one place to other place, the more volume of the natural gas is getting transported, which is having no additional energy content. Water is not having any energy. When we are transporting natural gas with the water, means unnecessary we are transporting more amount of the volume. So, even after the separator, when we are having the natural gas that contains significant amount of the water, and appropriate dehydration process should be chosen and designed to remove that water vapor that is present in the natural gas. And the selection of a dehydration process and the design criteria depends on primarily 2 parts. First is what is the amount of water the natural gas is carrying. Selection of the types of dehydration process and designing process will depend on that factor. Second is the presence of acid gases influence the water content treatment. So, if we are having a process that is chosen based on just water content, but if acid gases are also present along with the water. They will influence not only the amount of the water content is measured, they will also influence the process design and the overall process. When we say natural gas is having hydrocarbon and non-hydrocarbon gases, depend on the temperature and pressure condition, the amount of water that is present in the natural gas depends on the composition of the natural gas also. So, this slide shows here when we are having different gases like hydrogen sulfide, methane and carbon dioxide in pure state, the amount of the water they can contain at a particular temperature and pressure, we see the amount depends on the pressure as well as temperature. For example, in hydrocarbon gases like methane, that is the major constituent of natural gas, the amount of the water content at a particular temperature and pressure can be determined with the help of this chart. That says at a particular pressure, for example here, and a temperature let us say 100 degree F, this is the amount of the water content the natural gas or the methane can carry. This chart also shows when we are changing the temperature and pressure, the water content in the methane as well as in the other non-hydrocarbon gases also changes. That says, if we can change the operating temperature and pressure condition, we can see how much water content can be accommodated by the natural gas or by its constituent. We had seen here for the pure component, when it is a mixture, the behavior will be different, but the trend will be same, like overall when we are increasing the pressure, the water content is decreasing, and when we are reducing the temperature, the water content is decreasing again. So, the water content, that is the solubility of water in natural gas, increases with temperature and decreases with pressure, that we had seen for the pure component. Here we can see for a mixture that is considered as a representation of the natural gas, and from this Maketa and Behe method, that is represented in a graph form, that can also be represented in the table format, that says at a particular pressure and a particular temperature, what is the solubility of water, or other way, what maximum amount of the water can be present in the natural gas. And that we can see from this table, as we are increasing the pressure, the amount of the water content is decreasing. Similarly, when we are increasing the temperature, the amount of the water content is increasing. The similar data has been shown in this graph also. This is also from the Maketa and Behe. When we are having condition at the intermediate location, for example, here it is one for 15, 25 psi A, and if we want at 20 psi, we can always do the interpolation to get the data at a position which is not given in the table. Similar in the graph also, we can read it, that is more convenient way to get the data at a particular pressure and temperature. Both for a single component as well as a mixture, means natural gas, is showing with increasing temperature and decreasing the pressure, the solubility of water in natural gas increases. When it comes to determine how much water content is there, either we can read certain publication chart data available in the literature, or we can use a established mathematical procedure to calculate it. Here I am showing again from Maketa and Behe graph, that is for the sweet gas, means which is not having any sour component in it, like the H2S and SO2 primarily. In the water content determination, the salt presence in the liquid water also influence the water content calculation. Primarily, the water content in a natural gas decreases when the salt is concentration is increasing. So, the salt presence in the liquid water reduces the water content of the gas. So, from this slide we can see when we are having a natural gas, let us consider the natural gas as a sweet gas, and at a particular temperature and pressure data we can see the water content in the natural gas, and we can see at what temperature and pressure the natural gas is. We can read this chart and can say, for example, we are having a natural gas at 60 F and certain pressure, let us say that pressure is around 2000 psi. This is a 2000 psi line here, this point we can read the amount of the water content by the natural gas at that condition. The correction should be made primarily for the specific gravity, because this data is considered specific gravity as 0.6 and the specific gravity is different. Then we can use this inside chart that says at a particular specific gravity we can go vertically to a temperature condition at which the gas is, and going on the y axis we can calculate the correction factor that should be included for the specific gravity. Means when the gas is not having specific gravity 0.6, we have to make the correction factor for that. This is not only the composition of the natural gas that is in the form of specific gravity, but the salt concentration will also influence, and for that we can see another inside chart that says solid in the brine solution. If we can know, we can go vertical and choose the point where it is striking this inclined line, and we can see the ratio of H2O from brine by H2O from water. The correction factor that represent the H2O in the brine solution when the salt is present, or the H2O in just pure or mineral water, or means the water which is not having significant salt concentration in it. So, by doing this we could calculate the water content of the sweet gas. Now, if our gas is sour gas, we have to make the correction factor again, or we have to adopt the procedure that can give us the water content when the sour gases are present in the natural gas. For that purpose, what we can do, we can use this another chart that is given by Wishart and Wishart in 2003, and using this chart we can see what is the percent of that acid gases, or in the terms of H2S equivalent, that is account for both H2S and CO2 using this expression. And once we know that percent, we can see that percent and at what temperature our gas is. So, for example, that percent is just 35 and our gas is at 150 degree Fahrenheit, we can see Br here. From there we can go vertically up and see the line of pressure, let us say 2000 psi, and from here we can see on the y axis we can calculate the ratio, that say H2O in sour gas divided by H2O in sweet gas. So, from this chart on the right hand side we can get the H2O in sweet gas condition, and using the left hand chart we can convert this to estimate the H2O in the sour gas. All this is good or valid when the following conditions are met. For example, the pressure should be up to 10,000 psia, the temperature should be 30 to 350 degree, you can see from this chart where it is shown, and gamma g should be between 0.6 to 1.8, the chart is given only for that range, and H2S up to 55%. This is equivalent H2S in the natural gas. If that is matching, we can use this chart to get the water content of the natural gas. The same procedure we can write in the mathematical way. For example, the water content at 14.7 psi and 60 F from the chart assuming 0.6 gravity, as we seen in the last slide from the left hand side chart or from the Maketa and Behe chart, we can apply the correction factor for the specific gravity, for the salinity and once we know both the correction factor, we can calculate the water content, assuming the gas is just a sweet gas not having any sour gases in it. And for correcting the sweet gas to sour gas, we can calculate the H2S equivalent using this formula. Going this into right hand chart, we can calculate the point that represent the percent of H2S equivalent and the temperature. Going vertical on the upward chart, we can calculate the ratio that shows the sour gas to sweet gas ratio, and already we know water content in the sweet gas, we can calculate the water content in the sour gas. With this procedure, we are able to determine the water content in the sour gas. There is another procedure to calculate the water content, and that can be done by calculating the dew point. Dew point is the temperature at which the natural gas is saturated with water vapor at a given pressure. We understand from our phase diagram behavior, if gas is a mixture, it will give us the phase envelope when we are talking about PT diagram, and from this PT diagram we understand this is a dew point curve. And when we are changing the pressure, when we are increasing the pressure, this will go to liquid phase more than the gas phase, and when we are here, we are having mostly the natural gas in the gaseous phase. Similarly, if we are going at a higher temperature, we will go more towards the gas side, and when we are reducing the temperature, we will go or may enter again in the phase envelope and get the liquid. So, the same thing is applied when we are having the dew point calculation at a particular pressure. If we are able to change the condition and find out a difference between the dew point temperature of a water saturated gas stream before the dehydration or after the dehydration, we can calculate how much amount of the water content can be removed. And the difference between the dew point temperature of a water saturated gas stream and the same stream after it has been dehydrated is called dew point depression. So, the dew point depression can tell us how much water can be removed from the system. So, there are ways, there are procedures that allow us to perform the dehydration of natural gas. So, the dehydration system can be classified broadly in 4 major processes, that is direct cooling. When we are having the natural gas, if we cool it, because of the difference of dew point condition, the water component will get condensed from the gas and we can separate it. Compression followed by cooling. So, for example, when we are pressurizing the natural gas, again we will go to the two phase envelope system, where the water molecules will come out from the gas phase under high pressure condition, and by further cooling it, we can get the water separated from the natural gas. But both direct cooling and compression followed by cooling, like in this situation when we are having the inlet gas and outlet gas, when we are changing either the temperature in the direct cooling condition or temperature pressure followed by temperature change in the compression followed by cooling procedure, the water content here will be different, the water content here, and we will be able to get the water separated out from the natural gas. In most of the cases, it depends on the ability of natural gas to contain water vapor, decrease as the temperature is lowered at a constant pressure. That happens in the direct cooling procedure. So, in direct cooling procedure, we decrease the temperature at a constant pressure. During the cooling process, the excess water in the vapor state becomes liquid and is removed from the system, that we can remove from here. Cool the gas to a temperature below the dew point will give us the more separation. Cooling is used in conjunction with other dehydration process like the compression process, where compressing the natural gas will allow us to remove more water compared to just cooling process. Similar, by performing the absorption and adsorption process along with the cooling will provide us the better removal of water content from the natural gas. So, in that way we can consider the gas compressor as a dehydrator, because during the compression stage we are going to increase the pressure, and because of that the water will come out from the gas phase. In general, it happens the dehydration process of direct cooling and compression followed by cooling are not enough to remove the desired quantity of the water from the natural gas, and along with these two processes, it is often absorption and adsorption process are associated or are performed. So, what is absorption and adsorption process? So, they are the process to dehydrate natural gas up to certain level when it is matching the specification of pipeline transportation, and dehydration by absorption and adsorption practically remove the most of the water content present in the natural gas before it is going to pipeline or the transmission line. So, the absorption is a process in which water vapor is removed from natural gas by bubbling the gas counter current through certain choice of the liquid, those are having special affinity towards water, and those liquid are able to separate the water component selectively from the natural gas. Water vapor in the gas bubble is entrained in the liquid and carried away with the liquid out of the column where they are getting contacted. So, in absorption process, if we sketch here, we are saying counter current flow is happening. So, we are having natural gas or the wet gas. Wet gas means the gas which is having the water is going to a absorption tower, and from the top we are having a liquid or a selected liquid that is flowing downward, gas is flowing upward, they are getting contacted here in the absorber tower, where there could be either the trace kind of the arrangement or packed bed kind of the arrangement, and because of the contact here the gas becoming the lean gas means the water has been separated out, and the liquid is becoming rich liquid means it is having now water with it. In the adsorption process, we are having the similar kind of the arrangement, but the major difference between the absorption and adsorption process is, in absorption we are having a liquid that is having selectivity towards water and able to separate the water from the gas, while in the adsorption we are having a packing of a solid granular material or a bed of granular solid that is having affinity for water, and water is separated out from the natural gas with the help of that solid packing. So, if we say the nomenclature for this absorption and adsorption process, the vessels that allow either the absorption or adsorption process to take place is called the contractor or absorber. So, these vessels or the tower is a contractor or absorber. If we are talking about specific terminology, in case of absorption it is a absorber tower, or in case of adsorption it is a adsorption tower. But in general terminology it is called as a absorber or contractor. The liquid or solid that has affinity for water and is used in the contractor is called the desiccant. So, when we are having the absorption process, the desiccant is liquid, and when we are having the adsorption process, the solid packing is a desiccant. The two major types of dehydration process equipment based on the phases we are using, like the liquid and gas, we can say liquid desiccant dehydrator, also we can call it as absorption process, or solid desiccant dehydrator, it means it is a adsorption process. When we compare both, the solid adsorbent dehydrator are typically more effective than liquid, specifically the liquid is chosen is glycol dehydrator, and this is happened because the solid adsorbent are having more surface area because of their porous nature, because of the forces or the capillary forces they applied on the fluid or the gas that is passing through it, these solid adsorber are more efficient and more effective. While on the other hand, when the dehydration by absorption using the glycol is considered, it is more economical than the solid packing or the adsorption process when we are comparing the dew point, means the amount of the water should be removed is same. If you want to reach the water content of the dry gas means after the dehydration process, if we compare the dry gas in terms of water content, and if it is same, the absorption process using glycol liquid is considered more economical. We will see the major difference between the absorption and adsorption process in the subsequent slides. So, this is the adsorption process. The flow diagram shows all the equipment or the flow of gas through the symmetric diagram, and in this symmetric diagram we can say there are centrally two towers. There could be more than two towers. We can say this is number 1 absorber or number 2 absorber. That should be actually adsorber, because if we are having the solid packing here, the process is called adsorber, and we can say it is absorber or contactor. There could be multiple, because in the case of adsorption process, when we are performing the adsorption process to remove the water from the natural gas, over the time it is required to regenerate the solid packing, and when we are having just only one tower, it will be a situation when we have to shut down the operation, either clean the impurities those got stick to the solid packing, or just replace the solid packing. In both the cases we have to shut down the process. That is why always there are multiple towers, and 1 and 2 are in the operation, other are in the standby mode and or in the regeneration mode. When we want to switch to other tower, the previous tower that is got contaminated, or that is where the solid packing is not more effective as the time passes. So, we have to use another tower in the operation. If we look more closely here, we can see the central part is here, where the natural gas is travelling from here, and before natural gas goes to dehydration operation, it should pass through a filter or a separator, depend on the composition natural gas is having. If it is containing some solid particle, if it is having some liquid compound, those should be separated out before they are going to adsorption process or the adsorption tower, because those liquid will block the pores present in the solid packing and reduce the efficiency of the process. So, the gas is passing through some filter process, and you say this symmetric diagram includes several other equipment other than the adsorption tower. Those are required, we will see one by one. So, when the gas is passing through the filter, this is called the wet gas. So, we are having the wet gas here. Wet gas means it is having the water with it, and the wet gas can go either to this side or to this side. Assuming the wet gas is going to the tower first, and we are just operating only one tower, and when it is going from the top, it will pass through this packing of the solid. So, in the tower, gas is passed from the top, not from the bottom. The reason passing from the top is we are not going to disturb the packing of the solids in the tower because of the high velocity of the gas. That is why it is passed from the top, and when it is passed from the top, it will travel through this solid packing, and that solid packing could be because of the granular silica gel, bauxite alumina or activated alumina, or molecular sieves type of the material. The silica is having preference over the others because of it can tolerate the significant percent of acid gases present in the natural gas before it is going to be in a falling situation. And when it happens, what will be the situation? We are going to get the gas from the bottom part, and when this gas is coming out from the bottom, it may go till end and going to be a dry gas outlet, and this will depend on what is the efficiency of this adsorption process. If it is able to remove most of the water present in the natural gas, it is just a dry gas and it go to outlet. Here it is shown as another desiccant bed, where we are having the standby desiccating tower or adsorption tower, and in that case when this is in operation, it is going through the regeneration process. In regeneration process, what happens? Whatever the water molecules or the contamination in the natural gas, those adhere on the surface of the solid should get regenerated, so the tower can be used for the next cycle. And in that case, we have to make the arrangement in such a manner, a part of the gas is going through some heating process, and the heated natural gas is passing through the second tower or the regeneration tower from bottom to top, and we are able to remove all the impurities or are able to regenerate the bed for the uses. And when it is happening, natural gas got heated, and before it can be sent to a separation process, it has to go through a cooler. If the natural gas is having more temperature or natural gas is at a higher temperature, the amount of the water content will be high, means the separation will be difficult. That is why the natural gas should be cooled down before it is going through the process of dehydration, and that can be done using the cooler. We are having one regeneration gas scrubber also, and when we are removing the contamination from the natural gas, we have to have a separator from where we are able to get the water that is getting separated in the regeneration part should be able to collect at the end, and this will be the water to dispose. If liquid content is also there in the natural gas, that is also getting separated during this process, we have to have this 3-phase gas scrubber that can provide the additional option for the liquid separation. Otherwise, if we look in this sheet, we are having 2 towers, multiple towers could be there. With the desiccant bed packing, the efficiency depend on the packing it is having. There is a heater and cooler combination to heat the natural gas, so the regeneration process can be effectively performed, and then further cooling the natural gas, so it can go to dehydration process, and at the end we are having a gas scrubber which is able to separate the water out from the regeneration gases. In this process, if we see, the efficiency will depend on the amount of the natural gas that is getting dehydrated and the type of the packing it is having. The usual life of the packing is around 1 to 4 years, depends on the contamination as well as the water content present in the natural gas that is going through the dehydration process. And if we see the advantage of adsorption process, we can say lower dew point can be achieved, and that means we can get the dry gas which is having very minimum amount of the water content, and that could be up to less than 1.0 lb per mmCF. That is the advantage of using the solid desiccant. Again, the affinity, the impurities and the circulation rate will affect the process. Higher contact temperature can be tolerated. As we said, we are supposed to cool the natural gas before it is going to the dehydration unit, means the adsorption tower. Even the temperature of the natural gas is not that high, because of the solid packing, those are designed to tolerate the higher temperature. The higher temperature process can be tolerated, but depend on again the adsorbent chosen. Adsorbent means the solid packing. Higher tolerance to sudden load change, especially on startup. So, as we see, the packing of the solid get disturbed if we are having the higher gas flow rate from the bottom, We don't do that thing. Similar, if there is any sudden load changes happening, the solid packing may get disturbed, we may get the channel formation, and in case of the solid desiccant, we are having more tolerance for such kind of the chances, and that helps us when we are starting up the process or during the startup of the plant. High adaptability for recovery of certain liquid hydrocarbon in addition to dehydration process. So, this packing, for example, the silica granular silica gel packing, that is having the acceptability or adaptability for the other contamination. Those could be some higher hydrocarbon present or some solid particles in the natural gas. Those can also be separated out in the dehydration process. Certain issues are there as with any other process. So, the issues with the adsorption dehydration process are solid desiccant becomes less effective as they age, means over the time when they are getting used, because of the contamination present in the natural gas, because of the water is getting accumulated, they are going through the regeneration process at a higher temperature, the efficiency of those solid desiccant becomes less, and after certain time, usual life is 1 to 4 years, the replacement is required. It is a part of the process. Dehydration tower must be regenerated. As mentioned, there should be a standby adsorption tower which is under the regeneration mode, or it is already regenerated. So, it can be used when the first tower is put under the shutdown mode, and that should be regenerated and cooled for operation before another tower approaches exhaustion. Means when we need the second tower, it must be ready, otherwise the operation needs to be shut down. Hydrogen sulfide can also damage the desiccant and reduce its capacity, and that is the advantage of using the silica over the other desiccant, because it has more tolerance for the H2S. Sudden pressure surge may upset the desiccant bed and channel the gas stream, resulting in poor dehydration process. So, those issues should be taken care when we are going to design or going to use adsorption process for removing the moisture from the natural gas. Specifically, the pore size distribution in the desiccant, they should not get blocked permanently, or the regeneration steps should be operated in such a manner when the effective surface area of the silica particles or any other solid desiccants can be recovered to its original state. So, the efficiency of the dehydration process can be maintained. When we talk about another process that is widely used is the absorption process. So, the water vapor is removed from the gas by intimate contact with a hygroscopic liquid desiccant in absorption dehydration tower. The contact is usually achieved in packed or tray column. So, in the adsorption process, we are having the solid packing. Here in this type of the process, where we want the gas and liquid are getting contacted in a tower, we should have some arrangement where the contact time can be increased. That can be done by creating a packing with the inert material or arranging the trays in the column that we can see here. So, this is the glycol gas contactor. Mostly there could be several solvents used for such purpose, but the glycol has been widely used as effective liquid desiccant, and the 4 types of the glycols like the ethylene glycol EG, diethylene glycol DEG, triethylene glycol and tetraethylene glycol, or the combination of them can be used to perform the absorption dehydration process. So, this sheet is shown for the glycols, that could be either of them or the combination of them, and the glycol gas contactor tower is shown here. That says we are having the packing inside of it. This was for the tray type of the arrangement, where we are having the trays and allowing the fluid to travel from a certain section of this tray tower, and from bottom to top there is a significant room or the volume available to get efficient contact between the gas and liquid, and the liquid which is chosen is again having some hygroscopic, means specific affinity to water, and it will be able to absorb the water from the natural gas. And when it is happening, again the similar kind of the terminology we can follow. So, the gas, that is wet gas, means it is rich in water, is being sent to this absorption process before it goes to absorption tower. Again, if it is carrying some impurities like the liquid hydrocarbons, solid particles and others, those should be separated out with the help of some inlet scrubber. It is like a separator. So, the gas or the wet gas inlet is here. We are going to get the distillate outlet in this separator, and if we are having oil and water, free water I mean to say, then we have to use a 3-phase separator here. And after that, when this is happening, the gas from this scrubber or separator is going to flow from bottom to top in this absorption tower, and this liquid desiccant is flowing from top to bottom, and that is where the counter current flow is happening in this tower, and gas and liquid are in the contact. Because of the packing and because of the tray arrangement, the contact time can be adjusted to have the more efficiency of the process. So, the glycol that is coming to the system, we can say coming through this line glycol cooler, we can see the glycol that is getting regenerated or means getting purified before it is sent to the tower, and where we are having this contact, and from the bottom part we can say we are going to get the lean gas. Here it was the rich gas that was sent to the absorber. And what about the glycol or the solvent desiccant? So, the solvent desiccant that was sent here is lean, and from the bottom we are going to get the solvent which is rich glycol, means rich glycol means it is having more water. And when this rich glycol is coming, it may not have only the water, but some impurities, those are transferred from gas to glycol, and that is where first thing it should go through some filter arrangement. So, this is the place from where the glycol is or rich glycol is getting out of the tower. It should go through some filter unit where any impurities those enter into the glycol should get separated out, because it is going again to a pump and any impurities may damage the pump. And after that pump, it is sent to a flash separator, and this flash separator is able to separate out the gases. Those may have transferred from the natural gas to glycol, and the remaining glycol will go to further unit. And this bent gas, that may be methane or some other hydrocarbon gases, may be used for energy requirement or may be just bent out and discharged. So, the glycol that is here, which is carrying the water, it is a rich glycol, and this rich glycol is going to a heat exchanger, and after that it will go to a reboiler section, and in this reboiler section the glycol will get separated out from the water, and the reboiler operation is easy in case of the glycol solvent because of the boiling point difference. Water is having boiling point is around 100 degrees Celsius, we can say it is 212 Fahrenheit, and glycol is having around 204 degrees Celsius, means 400 degree Fahrenheit. So, because of significant difference in the boiling point, we can easily separate or boiled off the water from the glycerol, and in that case a reboiler is required, and the energy for the reboiler can be provided either from the external fuel gas or the gas that is produced in the flash separator. So, a part of that can also be used to energy required for the boiler. Before it is going to burn in the boiler, it has to pass through a scrubber to take out any impurities in the gas. And when the separation is happening, we can say in this stripping still a long tower, because of the self reflux, the water will go out because it has low boiling point, just 100 degrees Celsius, and the glycol will fall down here and get accumulated in this region. And from here, because of the arrangement, it will go to heat exchanger place, get heated, it will transfer the heat to the glycol that is passing here. So, one is flowing in the shell, another is in the tube, and the arrangement can be done based on the heat transfer calculation, which one should go to shell side, which one should go to tube side, and we are not discussing the heat exchanger in detail, but the arrangement is done in such a manner. So, the glycol that is here reduce the temperature little bit by transferring the heat to this glycol, rich glycol that is going through this flash separator. So, the lean glycol and rich glycol are exchanging the energy, and further here it is coming to this section where the glycol cooler, which is having the natural gas or the dry gas, is passing through it in the shell side, or in the tube side we are having the glycol that is hot, that is further getting cooled down, and when it is happening, then it is going to tower at a desired temperature it needs. And in this process, overall we can say we are having the inlet scrubber here, we are having one scrubber at the end also, where we are able to separate the rich glycol and the gas if any present, and in between we are having one absorption tower, a reboiler, where we can concentrate ethylene glycol by removing the water vapor, and we can recirculate the glycol here. So, the efficiency of this process compared to adsorption process where we were having the solid, first thing is it does not need to shut down the process or additional tower. The regeneration is done in terms of reconcentrating the glycol. If any losses of glycol may happen because we are exposing the glycol to higher temperature, makeup of the glycol is easy compared to solid dehydration process, where we have to change the packing after certain time. And in this process, the reboiler is operated around 350 degree Fahrenheit, and we are able to reconcentrate glycol up to 99.5% or better. The losses can be managed by making up the glycol to this process. We can use either a single type of the pure glycol, or we can go with a combination, but from the studies conducted, TEG has gained nearly universal acceptance as the most cost effective of the glycol due to its superior dew point depression, operating cost and operation reliability. The dew point depression can be achieved up to 40 degree F to 140 degree F, means significant water removal can be performed with the help of TEG, and in the pressure range of 25 psig to 2500 psig, and gas temperature 100 to 160 degree Fahrenheit. So, this can be operated. We cannot expose to a higher temperature, because in that case the degradation of glycol may happens, and when the glycol is getting degraded, certain chemicals may get formed and those will contaminate the entire operation. So, we should not exceed or we should not expose to a very high temperature condition, but within this operation condition we can achieve significant dew point depression. The dew point depression depends on the equilibrium dew point temperature for given TEG concentration and contact temperature. So, at what temperature the natural gas is getting in contact depends on the Tg concentration and the temperature, the water removal can be achieved. Again, the water removal can also be represented in the form of dew point depression. So, if we understand at what temperature and pressure the gas is at one point and at what the condition on the other point, if we can calculate the dew point at this condition and the new condition, we can calculate the amount of water is removed from the natural gas. Very hot gas streams are often cooled prior to dehydration to prevent vaporization of TG. In that case, we will lose the solvent or the liquid desiccant, I should say, triglyceride in this case, and if the vaporization of the glycol is happening, we have to add as a makeup from the outside, and that will include additional cost to the process. So, if we compare, as mentioned previously, if we compare the adsorption process with the absorption process, we can see the adsorption process can be more effective because the solid packing desiccant can go from 1 year to 4 years, and the selectivity of that packing towards water molecules allow us to perform the efficient process in terms of water removing. But if the water removal is same in both the process, this process is more economical because only thing we have to add the makeup glycol, not replacing the entire packing as in the case of the solid dehydration process. So, if we specifically talk about the absorption advantage, so the glycol dehydrator, considering glycol as a liquid desiccant to perform the absorption process, it offers several advantages like the low initial equipment cost, low pressure drop across adsorption tower, makeup requirement may be added readily easily for the glycol that may get vaporized over the time if the temperature is high, or it may lost little bit in flash separator or somewhere. The plant may be used satisfactory in the presence of material that would cause falling of some solid adsorbent. As mentioned, the solid adsorbent or solid desiccant may get fall because of the some contamination. Those are going to block the pores. It means going to reduce the effective surface area of the solid desiccant available. So, if those kind of the chemicals or substance are present in the natural gas, it is a better option to use the absorption process compared to adsorption process. Glycol dehydrator also presents several operating problem like the adsorption process or like any other process. When we are talking about the advantage, there are certain issues also with any operation. So, for the glycol dehydrator, if the suspended matters like the dirt, scale formation, iron oxide present, they may contaminate the glycol solution, and if it is happening, the efficiency of the process will go down. More care needs to be done in terms of the putting the glycol filter, the pump that may get damaged because of the impurities present, flash separator where we are just considering only the gas is going on the vent and rich glycol is going through this reboiler heat exchanger, then the reboiler step. So, every place if the impurities are present, the efficiency may get down, and we have to be more careful in taking the action to separate out these impurities. Overheating of solution may produce both low and high boiling decomposition product. So, for example, if we are having the TEG, decomposition of TEG may produce different compounds, and those are going to take a part in the absorption process, and the process will become less efficient. When both oxygen and hydrogen sulfide are present, corrosion may become a problem. That is a universal problem when we are having the water and hydrogen sulfide together, the problem of corrosion will be there. Highly mineralized water with inlet gas may over the long time period crystallize and fill the reboiler with solid salts. So, if the water that is present, which is having also some significant minerals present in it, that is getting separated with the glycol, going through the flash separator, then going to heat exchanger, then finally to reboiler, where the water is getting out because of the evaporation process, those minerals will remain in the glycol phase, and if that is the case, they may create a problem. To start a plant, all trays must be filled with glycol before good contact of gas and liquid can be expected. So, this is the operation problem that happens with any type of the gas liquid contact in a tray packed or column packed tower. That will also be in the case of dehydration absorption process. Sudden surges should be avoided, as mentioned in the adsorption process also, in starting and shutting down a plant. Otherwise, large carryover losses of solution may occur during the process. So, if we compare absorption and adsorption process, certain features are same and certain advantages are offered by the adsorption process and certain advantages offered by the absorption process. When we talk about the design aspects, we can discuss the absorption process for its design application. So, the glycol dehydrator design depends on certain factors that determine what size of the tower should be, what should be the diameter, what should be the capacity of the associate devices like the separator at the inlet, flash separator, reboiler duty, heat exchanger dimensions, glycol cooler, all depends on the gas flow rate that is going to be dehydrated, the composition of the gases, or in terms of the specific gravity of gas, at what pressure the gas is going to be treated, and the maximum working pressure of contact. So, when we are making the gas liquid contact in the tower, at what pressure that is happening, gas inlet temperature, at what temperature the gas is entering to the absorption plant, and outlet gas water content required. That is the most important one, the outlet gas water content, and that means the dew point depression, what dew point depression should be achieved, and up to what level the dry gas after this dehydration process should be made dry, means the less water content determine the specification or the design aspects of the absorption process. Certain criteria are mentioned here. So, at least one of the following two design criteria should be or must be employed when we are talking about the process or absorption process that is designed meeting one of the criteria or not. If not, certain measures should be taken to make this process more effective, more efficient, more economical. So, for example, glycol to water ratio. So, when we say this much percent of the water content is present in the natural gas, we want to reach to certain percent of the water content by removing the water from the natural gas. How much amount of the glycol circulation should be employed to achieve that target? And it is said the GWR, glycol to water ratio, should be in the range of 2 to 6. So, 2 to 6 gallon TEG per lbm of H2O. It should be in the range of 2.5 to 4 for the field dehydrator operations. So, the GWR becomes important, otherwise if we are having more circulation of G compared to the water we are removing, the pumping cost, the size of the equipment that is going to deal with the glycol like the flash separator, the reboiler, all things will add up the cost to the process. Lean TEG concentrations, when we are talking about reconcentrating or recycling the TEG back to the absorption tower, we should design the process that is meeting the recovery or reconcentration in the range of 99.0 to 99.9% lean TEG. Lean TEG means the water is not there. A value of 99.5 percent lean TEG is utilized in most design. So, the design of the entire absorption dehydration process should be done. We are able to recover 99.5% glycol or the TEG from the process, sending it for the recycling purpose. So, when we talk in detail of the design parameter for the absorption dehydration process, we are not discussing about the mechanical aspect, but what should be the size of the equipment that is going to be used to achieve the desired dew point depression. So, if we talk the first unit that is installed in the dehydration absorption plant is the inlet scrubber. Mostly it is with the height of 7.5 feet. For the diameter, it depends on the gas that is going to pass through it and the operating pressure it is getting operated. Based on that, we can choose the diameter of the inlet scrubber. It is similar to the separator, where we are having the separator pressure at which it is going to be operated and the amount of the natural gas it is going to deal with. The diameter should be chosen. We already know the height, or we already fixed the height 7.5 feet, and the volume required to accommodate that gas will be calculated, and the diameter can be calculated from this chart given by Sewalls. This is given at a particular specific gravity and temperature. Different chart may be obtained for the different conditions. Second unit that is important is glycol gas contractor. Again, the standard height consider for this absorption tower, which is having the tray and the packed bed to provide the more contact time for the gas and liquid. For that, the minimum required diameter of the contactor can be determined based on the gas capacity of the contactor and standard gas 0.7 specific gravity at this temperature. So, similar what we are having here, but in this case we are not having the standard gas or the gas with a 0.7 specific gravity, we are having a different temperature also. So, the correction for the temperature and the specific gravity should be included to calculate the gas capacity at the operating condition, and the correction depends on the type of the gas contactor we are using. It is a packed bed or it is a trade. There are several tables reported in the literature. The temperature correction CT can be done depending on the temperature it is getting operated. So, we are having the temp table where the several temperature data are there, and accordingly the correction for the temperature can be included in the expression. Similar for the specific gravity, for specific gravity also what gravity we are having for a gas we are dealing with, the correction factor are available in the form of table in the literature. But again, different correction factor will be applied for different arrangement. For example, trade or the packed one. Knowing the correction factor, knowing the standard condition and 0.7 specific gravity gas at 100 degree F, we can calculate the amount of the gas that is going to be deal by a gas contactor. The height is already fixed, we can calculate the diameter. Important parameter is how much water has been removed from this tower or absorption process can be calculated by this expression that says Cwi minus Cwo multiplied by the Q, that is the gas flow rate. Cwi is water content at initial gas, that the wet gas, and Cwo water content of the outlet gas, that is the dry gas. If we take the difference of that multiply by the gas flow rate divided by 24, that is just for conversion to unit, because the water removal is calculated in terms of hours, while the gas flow rate in terms of the per day, we can calculate the amount of water that could be removed from this process. And to remove that water, how much glycol circulation rate should be, we can calculate knowing the GWR if multiply GWR with the CWI, initial water content of the wet gas, multiply by the gas flow rate, we can get the glycol circulation rate to achieve the water content required in the dry gas or desired dew point depression. Other things, those are involved in the absorption dehydration process, like the flash tank, which is separating the rich glycol from the gases, if any. The dimension can also be calculated from the literature data, knowing the amount of the glycol that is going to be dealt by that flash separator. Similarly, we can do for the reboiler duty, how much energy should be supplied to reboiler if this much amount of the water and glycol is going to be separated at the reboiler condition, and what should be the volume going to behave like a storage, and from where the lean glycol is going to transfer to heat exchanger device, and further it from a cooler it is going to the absorption tower. So, in this lecture we had understood the several dehydration process, starting with the cooling, compression followed by cooling. Both depends on just changing the temperature and pressure condition, and the water or the dew point of the natural gas will get changed, and accordingly the water can be separated out from the natural gas. Further, we understood the adsorption process, that is based on the solid packing in the column, and in detail we understood the absorption process. And altogether we can say, by performing the absorption and adsorption process, most of the water present in the natural gas can be dehydrated, and we can get very minute amount of the water present in the natural gas that is passing out of the dehydration plant. There are processes where the CO2 H2S can also be separated out along with the water, but those processes face the problem depend on the type of the process chosen. We will discuss the sweetening processes, removal of H2S and CO2 in the next lecture. With this, I would like to end my lecture here. Thank you very much for watching the video. We will meet in the next lecture. Thank you.